Sir, good morning.
Good morning, ma'am. Am I audible?
Sir, you're audible, sir.
Yes, ma'am. Yes, ma'am.
Shall we start the session, sir?
Yes, ma'am. We'll start.
Good morning, everyone. Welcome to the final day of our faculty development program on quantum computing. Over the past 6 days, we have explored the exciting and ever evolving world of quantum computing, from fundamental principles of quantum mechanics to the groundbreaking technologies that are shaping the future. We hope you enjoyed the deep dives into quantum algorithms, quantum hardware, and real world applications, and are now equipped with a solid understanding of this transformative field. Today, as we wrap up, we will continue our exploration with some final insights into the future of quantum computing and its implication in various industries. We will also engage in hands-on activities, apply the concepts we learn, reinforcing our understanding and sparking new ideas for integrating quantum computing to our academic and professional work. Before we dive into the today's session, we would like to extend our heartfelt gratitude to the organizers of this incredible FDP. Their hard work, dedication, and attention to detail have made this event a truly enriching experience for all of us. This program has been wonderful opportunity to expand our knowledge on quantum computing, and we are grateful for the resources, session, insightful participants who joined for our learning journey over the past week. Let us make most of our final day together. Before we begin the session, I feel an immense pleasure to introduce today's guest, Dr. Jay Kumar. Dr. Jay Kumar, a prominent
Hello.
in the field of quantum computing, who brings a wealth of knowledge, experience as our speaker for today's session. Dr. Jay Kumar is an IBM quantum educator and IBM Qiskit advocate mentor, roles that have made him a leading voice in promoting quantum computing education and engagement globally. His involvement in quantum community extends beyond India, where he is actively building a network of researchers, educators, and enthusiasts, fostering the collaboration and learning in the field of quantum technologies. As a certified associate developer in quantum computation, Dr. Jayakumar has developed deep expertise in utilizing Qiskit, IBM's open source quantum computing framework, to unlock the potential of quantum computing. With over 15 years of experience in research and lecturing at the university level, Dr. Jaikumar has significantly contributed to both academics and the industry. He is an active senior IEEE member and contributes to the IEEE quantum standards, which positions him at the forefront of shaping global standards in quantum computing. Throughout his career, Dr. Jaikumar has authored more than 15 research papers in international peer-reviewed journals and conference proceedings, contributing valuable knowledge to the scientific community. His dedication to advancing quantum computing research is further demonstrated by his role as a technical paper reviewer for prominent IEEE quantum conferences. Dr. Jayakumar's passion for quantum computing extends beyond research. He has conducted over 50 quantum computing programs across multiple countries including India, the USA, Russia, and many more. These programs include faculty development program, quiz-kit training program, and the awareness camps, empowering the educators, researchers, and the industry professionals to explore and implement quantum technology in their respective field. We are privileged to have such an eminent speaker with us today, and we look forward to his insights and expertise in quantum computing, which will surely inspire us and motivate us to continue our journey of learning in this transformative field. We welcome you, sir.
Thank you for such a wonderful introduction, ma'am. I thanks all the organizer. I thank all participants eagerly attending this program. So let's dive into topic.
Yes, ma'am.
Yes,
Yes, sir, we can start.
yes, sir. Thank you, thank you. So, good morning to one and all. I am serving as IBM Quantum Educator as well as IBM Quiz-Kit Advocate Mentor. So today we're going to see about introduction to quantum computing, and we can have hands-on on Quiz-Kit software. Okay. So teaching this course or handling this course is quite difficult. So what I did, I got permission from Ms. Geetanjali Venkatraman. She is working as a thought work illustrator in UK. She created a beautiful PDF file which is handmade. So I got her permission. I converted those PDF files into animated PPTs. So this is the disclaimer I want to do. So why we need quantum computers? This question we need to ask for ourselves to do anything beforehand. Okay. So we have supercomputer, we have mainframes, but why we have quantum computer? Because whatever the computation power we are giving, it is not able to solve all types of complex problem. Okay. So it started with the fundamental question of how long Moore's law will hold. Okay. So quantum computer not intended to use replace the classical computer. Instead of that, it will help to enhance the computation capacity. Okay. So anybody can describe what is the meaning of Moore's law? Is participant allowed to answer, or shall I start?
This Moore's law is applied in the CPU transistor integration, if I'm
Yes,
right.
ma'am. Exactly what you say. So Moore's law is predicted by Jordan Moore, one of the co-founder of Intel Corporation. Okay, in 1965, what he predicted, each and every 2 years, the computation power will get double. Okay, so this is the fundamental thrust of all CS and IT industry. Okay, so without this law, nothing will survive, right? So if you take look at the processor, which is the building block of the computer, okay, so processor become cheaper and cheaper and smaller each and every 2 years. So this should be continuous. So because of this, every company able to afford advanced processor, they can upgrade themselves. So normally the processor contains billions of transistors. Suppose if each and every 2 year company not able to upgrade the processor, they are not able to get the speed higher level processor, they able not to get projects. Okay. So what is the problem of creating the billions of transistor in a processor? Each and every 2 year, you need to reduce the size of transistor. Okay. So this is become true and made available only if you able to miniature the transistor size. Okay. So now look at the smallest example. So transistor is the simplest form of processor. So this will act like a switch. It will allow your electron to stay, or it let you to flow. Okay. So it will act like a switch. So normally the size of transistor is less than 10 nanometer. Okay. So if you reduce the size less than 4 nanometer, what will happen? If we try to create a transistor less than 4 nanometer, what will happen? Anybody knows the answer?
Sir, actually, we are blocked with the participant mic. Actually, if they raise the hand raise, then they will unmute and ask the questions. So,
Great, sir. So
if
normally,
any part, please, any participation, sorry, if any participant, if you have any doubts, please raise your hand. I unmute the mic, then you can ask the questions.
so I can do like this, sir. What I can,
Please. Hello, sir, you are not audible. Sir, you are not audible.
now I am audible.
Ah, yeah, yes.
Yeah, sorry. So if
Actually,
you
the
try to,
security purpose, we actually blocked all the
yeah,
participants.
I can understand, sir. I can understand. So if you try to reduce the size less than 4 nanometer, quantum effects will come into play. So we are hitting the nature's bottom limit. So what is this quantum effect means? Okay, the quantum tunneling will make electrons to jump and flow even the switch is off. So this is the beauty of the quantum physics. Okay, imagine if you try to stay your data in on state. Okay, if you try to create transistor less than 4 nanometer, this quantum effect will come, quantum tunneling will happen. This will make electrons to jump and flow even the switch is off. Imagine if the switch is on, your data is turned into off level automatically without your control. Without your control. So this is weird. You cannot make your data stable. You cannot believe your computation. Okay, when quantum tunneling happens, it will convert 0 to 1 and 1 to 0 automatically without your control. You cannot believe your system computation. So that is why we are not able to reduce transistor size. Whole semiconductor industry will go to stagnation level. So this will affect all domains, especially CS and IT. Right. So we'll discuss what is the meaning of quantum. So quantus is a Latin word, stands for how great. Okay, the same word used for to represent to mention smallest piece of energy. So where you can find smallest piece of energy in subatomic levels. So energy between electrons, energy between ions, those interaction, pulling energy and reflecting energy. So everything can turn with the help of quantum. So this will act like a prefix. Right. So if you want to describe nature at the tiniest scale, you need to have quantum mechanics. So whatever the mechanics we studied in our school or colleges, in our college, it is about classical mechanics. So what is available for a naked eye? Okay, what is visible for naked eye, you can observe, you can understand, and you can describe with the help of classical mechanics. But quantum mechanics is subatomic level. So we are not able to witness it. We are not able to understand it because we are not familiar to it. So our whole evaluation is based upon classical level, okay, not subatomic level. So this is why the people who try to understand quantum feel it more difficult, feel it more weird, feel it more absurd. Okay? They are not able to understand initially. Okay, so if you put all these topmost scientists together, Einstein will hold the first rank because his contribution for calculus, contribution for calculus. And there is an interesting section why he invented calculus because of he identified gravitation. Okay, he able to understand why it is falling down because the mass of apple is very less. The mass of apple is very less, where in case of earth is very huge. Okay, so because of huge difference, earth is able to attract apple towards it. Okay, because of less mass, the apple is not able to pull Earth towards it. So each and every particle in this universe will exhibit own gravitational force. So proportionally to its mass, right? So once you understand the gravitational force, once you're able to calculate the factor, gravitational factor, then you're able to define acceleration. Once you're able to define acceleration, you can define inertia of an object. So these are consequences. Once you're able to do one thing, it is like a domino effect, chain effects, right? Then you can easily describe velocity, momentum. So everything is interrelated, right? So whatever the law applicable for small objects, equally applicable for larger objects. So this is about classical mechanics, right? So from this diagram, you're able to understand everything is predictable in nature. If you understand one phenomena and try to relate for much more complex ranges. Okay. So this is what we are doing using classical physics. Classical physics for prediction. If you try to do with the help of software, with the help of data set, it becomes machine learning. So if you want to master machine learning, if you want to create perfect algorithm, we need to use physics law, physics inspired algorithm. So this is what I mean to mention over here, right? So if you want to understand the comparison between quantum and classical, these will set apart. So whatever the law applicable for classical, okay, it will not implement in the same way in quantum. So these will differ. Okay, both classical world and quantum world are entirely different. Law will operate in different level. So this make difficult to understand it, to explain it, right? So we'll start with the basic what we covered in school about the simple experiment, duality of nature, right? So we have two set of experiments. One is particle experiment, one is wave experiment. In particle, what we'll do, we'll take a full bucket of sand and we'll pour over a slate which contains two holes, and this will make two distant piles. Can anybody reason out why it is forming two distant piles? Why it is forming two distant piles? Can anybody reason out? Hello, am I audible?
Yes, sir, you are audible, sir.
Yes, sir.
1 minute.
Hmm. Why it is making two distant piles? Because of
Anand?
particle nature. No issue, sir. I will continue.
No, sir. One
Be-
more participant actually have a doubt. Sir,
okay,
unmute
okay.
and ask a question, sir. Anand Stephen, sir. Okay, sir. You can do this.
Yes, sir. So because of particle nature, each and every sand grain is independent and free to flow. Okay. Because of gravitation, it is falling down towards to the second plate. Okay. So it will form distant piles. So after some point of time, it will slide away. It will slide away. Right. So if you understand the material, if you understand the physical phenomenon, you are able to understand why it is happening in this particular way. Okay. So do the same experiment in terms of water. Here we are changing the material from sand to water. Sand to water. Now water is a continuous wave. Okay, it is like a medium. It will act like a medium. If you try to tap in one side, okay, if you try to tap in one side, this waveform will generate in two slits in the same pattern. So it will split up. It will go in two slits. So at some point it will form darkened bands. Some point it will form lighter bands. Okay. So this is due to interference. Now, if you do the same experiment, same type of experiment in quantum, okay, you'll get unexpected result. Here you can understand. Here you can understand phenomena. You can understand phenomena and reason out, because everything is understandable, everything is relatable. But if you do in quantum world, the result will be unexpected. You cannot explain also. So this is the fundamental difference between classical physics and quantum physics. Now we try to start experiment with the form of light. So we have one blackboard. We have one light source. Okay. Once you shown light, okay, the light will have the continuous property. So light will travel in continuous waveform. So again, it will go through these double slits. Whatever experiment we covered in previous slide, we do the same experiment setup. So slit 1 and slit 2, with the help of slit 1, slit 2, it will form the same pattern, wave nature. Okay. At some point it will interfere. At some point it will go align. So you will get continuous band like this because of interference pattern, right? So we'll move to next slide. Okay. So this type of experiment will reveal wave-like nature, wave-like nature. All right. If you add little bit additional equipments, detectors. So with the help of detector, you are able to open and close. You are able to open or close this slit. Okay. So if you do, it will behave particle-like nature. Particle-like nature. So this is exactly like sand experiment. This is exactly like water experiment. Okay. So what you can conclude from this experiment, if you are not looking at your thing, if you are not looking at your experiment, okay, if you are not observing, okay, uh, sorry for interrupt, it will spread like a wave. It will appear like a wave. If you try to observe, if you try to open and close one of your slits, it will behave like a particle. So your wave will collapse and it will reveal like a particle. Are you able to understand up to this slide? Shall we move? Am I clear, audible?
Yes, sir.
Okay, thank you, thank you. Now we can do the same experiment with the help of electron gun. Here we are ejecting electron one by one, just like particle, just like particle. Okay, here we are ejecting electron one by one. Sometimes it will go in slit 1, sometimes it will go in slit 2. Okay, consider your electron like a ball. Okay, but your output is like a wave nature. Even though you're sending your input in particle, your output will be appear like a wave. So in classical, it is not possible because the electron only go in slit 1 or either in slit 2, not at the not both at the same time. But if you look at quantum world, if you look at quantum world, the electron can go through both slits S1, S2 simultaneously. So this is not possible in classical because one ball can go through only one hole at a time. But here the same ball can go through both holes at the same time. So this is the fundamental difference between classical and quantum. That is why we got output like wave nature instead of particle input. Okay, single input. Okay, so that is why the quantum physics is very, very unpredictable. So outcome of a quantum experiment nearly impossible to understand nor to explain. You cannot understand because it behaves in this way, mysterious way. Okay, so this is the fundamental difference. If you understand this slide, we can go further. So quantum depends upon two principles. One is superposition, the another one is entanglement. So this will act like a basic building block to understand quantum. Okay. So superposition, you can consider a quantum particle, a subatomic particle. It could be any subatomic particle, just like photon or electron. So this will spread like a wave. This will spread like a wave, right? So imagine if electron is spreading like a wave, if you want to tell its location, if you want to predict its location, so at this point you have 45% of chance. So at this point you have 30% of chance, right? So it will exist in different location with different probabilities. So this is what it means. Okay. So if you want to know its location, okay, or state of that quantum particle, then you need to add all this location and need to calculate all this probability together. So you need to sum all these probabilities. Okay. So just like adding waves in the water to form a resultant wave, you need to add quantum states to add up to form a superposition. So in simple terms, I try to explain what is superposition. One position over another position at the same time. So this is the simplest definition I can give right now. So superposition is nothing but one position over another position at the same time. If you want to know quantum state, you need to add all these positions together, all these quantum states together. Right. So we'll have some example. So to explain quantum, sometimes we need to have classical physics example. Right. This is very, very simple. If you understand, you try to relate with quantum. So this is about tossing a coin. A coin contains two states. A coin contains two states. So one state is head, one state is tail. Okay. So what is the chance of getting head? 50% chance. If you are flipping, if coin in the middle of the air, so 50% of chance you'll get as head, 50% of chance you'll get tail. Okay. When you can sure, when you can say 100%. Can you tell the answer? When you can say whether the head is 100% or tail is 100%. Anybody able to answer? When you stamp that coin with your hands, when you stamp or allow that coin to freely flow, allow that coin to settle in ground, then observe, then observe or look at it, or look at it. Now you can say with 100% whether it is head or whether it is tail. Okay. So try to relate this experiment with Schrodinger cat. With Schrodinger cat. So this is a black box. So this is a black box. You cannot see. You cannot see inside this block. Inside this box. Okay. Then what you did? You placed one cat, one live cat, one radioactive nucleus. Okay. So we don't know when this radioactive nucleus is going to decay. Going to decay. We don't know. We don't know when it is going to decay. Suppose if this radioactive material is going to decay, this cat is exposed and the cat will go in dead state. If it is not exposed, this cat is stayed in alive state. So we don't know what is the state of cat until you open that box, then you observe that box. Okay. If you open your box, if you open this box, then the state of cat is dead become 100%, alive become 0%. Or other chance, the state of cat become dead 0%, alive 100%. So there are two chances of cat, two states of cat, either alive or dead. But inside box, it is in superposition. So what is the chance? 50% for dead, 50% for alive. So inside box 50% and 50%. Okay, if you are not looking. Now you can attach this example to little complex. Cube contains 6 faces. So each side colored differently. If you are observing from this angle, orange will appear like a front face. If you are observing from back side, blue will appear like a front face. Okay. So cube contains 6 faces divided into 6 equal probabilities. Equal probabilities. Okay. So imagine if it is a quantum state, you need to add all these states together to have 100% result. Okay. So compare all this stuff to electron. Compare all this stuff to electron. It is like a cricket ball. It is like a cricket ball. If ball spin upwards, so make it state 1. If ball spin downwards, make it to 0. So we are attaching 0 and 1 to a cricket ball. Okay. Sometimes if cricket ball spins diagonally, if cricket ball spins diagonally, then you can call it superposition. So 50% chance for 0 and 50% chance for being state 1. Okay. So this is the simplest explanation of superposition. Then we can build with entanglement. So entanglement stands for strong correlation. Strong, sorry about that. Strong, it is not recognizing. Strong correlation. Okay. So if you take 2 electrons or 2 photons or any 2 subatomic particles, make strong correlation between them, make strong correlation between them, then it will form entanglement state. It will form, sorry, it will form entanglement state. Okay. So what it means, whatever happens for one particle, we can see the same phenomena in another particle. So whatever happens for electron 1, same effect will happen in electron 2, right? So this is called entanglement. Okay, so once you created entanglement, once you created entanglement between two particles, then you can separate these particles to different universe. So one particle in one universe and another particle in another universe. So what you can do with the help of this phenomena, you can communicate easily. You can communicate very easily in speed of light. So normally if you do quantum communication, okay, there will be very little delay. Okay, it will travel in the speed of light. So if you want to understand this phenomena, you need to understand normally rock, paper, scissors. So instantly you able to know the state of the other player in this game, right? In the same way, if you measure one particle, you'll know information about another particle. Information about another particle. Okay, this is very exciting. Now
Sir,
China demonstrate.
sir,
Yes, sir. Yes, sir.
excuse me, sir.
Yes,
Is this entanglement tested, sir, anywhere in
tested,
a
sir.
different
That is
universe?
not universal. We are not able to move the universe now. We are not able to move
Yes,
that
yes.
far. This is for theoretical aspects.
Okay, sir. Okay,
Even
sir.
though if you can move to different universe, it will work. So it is worked in laboratory condition. So China demonstrated satellite to Earth,
Yeah,
satellite
yeah.
to Earth, and DRDO they demonstrated Earth station to Earth base station to satellite. So it is
Oh,
provable. It is
it is.
demonstrable.
Oh, okay, sir. Yes.
Great,
So
sir.
there are experiments going on.
They are building, sir. They are demonstrated quantum communication will happen.
Okay,
It will
sir.
happen.
Okay. Yeah, thank
100%
you.
sure.
Yeah,
Thank
thank
you,
you.
sir.
Thank you. Thank you.
So this is what I explained in previous slide. So imagine you have electron 1. Imagine if you have electron 2. If you make strong correlation between them, very strong correlation between them. Now both electrons in zero state. Now both electrons in zero state. Okay. Now you are separating those electrons in different places. Imagine if you are having two electrons in Chennai, and if you are moving one electron to Coimbatore and one electron in Chennai. So Chennai electron, whatever happens for Chennai electron, you can see same effect, electron kept at Coimbatore. Now it is moving to 1. Okay, you can see the same transformation in Coimbatore also. Suppose if you move this electron to 0, okay, automatically this electron will show the value 0. So this is called entanglement. So if you make two electrons in entangled way, you can communicate very easily. Right. So what is quantum mechanics good about? You can build strong laser. Okay, you can build quantum computer using laser. You can build quantum computer using laser. So it is about photonics. It is about photonics. So China heavily investing in photonics based quantum computer. It nearly invested 15 billion US dollars. 15 billion US dollar. Where in case of USA invested 3 billion. Where in case of India invested only 1.2 billion. So you can see vast difference between India and China. China went ahead 15 times. 15 times. But mostly China tried to build photonic based computer, quantum computer. Okay, so this will help you to build energy efficient nuclear reactions. It will able to build better VLSA design. Okay, it will able to build better efficient transistors. Okay, it will be uh, make humongous changes in medical devices. In future, we'll have very accurate scanner. Okay. So before this PPT, what I want to show, the quantum computer architecture. So this will give you clear idea how a quantum computer will look like. Whether my screen is visible, I am showing image instead of PPT.
Yes, sir. Yes, sir. So,
Okay. So this is how quantum computer look like. You can imagine it is like a golden cylinder. Okay. So this is made up of mercury, gold, copper, whichever material have superconducting property. They will use those material to construct machine like this. So each and every layer, you can see this layer. So this will decrease temperature at the core. At the core, you will get absolute zero temperature. So minus 273 degrees Celsius. So this is how quantum computer look like. Uh, this is the architecture, and it is covered by a shield like this red color. So this is acting like a cryogenic engine shield, like a rocket engine shield. So this will maintain the coldest temperature. Okay. If you are looking at the processor will be locked at over here. Your quantum computing processor will be locked over here. So all the signal is translated in this tiny processor module. So what are you are looking at this whole architecture? It is act like a refrigerator. It is acting like a cooling fridge. So this will give a rough idea about how quantum computer acts. So we'll discuss what is the architecture of quantum computer. This is what I shown in the diagram. This is one of the way. So you can build 1,000 different types of architecture for quantum computer. Okay, we are dealing with only one architecture. So quantum computer is made up of quantum particle. Again, we all know what is the quantum particle. So it will act like a qubits. It will act like quantum bits. So it could be an electron, it could be an photon, it could be an ion, it could be any subatomic particle. It could be any subatomic particle, right? So each and every particle contains different properties, like a spin, like polarization. Okay, take an example of spin. It can spin upwards or downwards. So if you take polarization, either horizontal or vertical. So in superposition, it is in diagonal or in between up and down. Okay, in same way, it is in diagonal. Able to get the idea? So quantum computer is made up of quantum particle, which is the core for your quantum computer, which will act like a quantum bit. We can use any subatomic particle like electron, photon. So according to your chosen quantum particle, your architecture will differ. So this architecture meant for only electron. Okay, what I am showing in this architecture, it is only for electron. Okay, so this electron contain spin. If you are choosing your quantum particle like photon have this polarization property. So each and every quantum particle have different property, and we are using this different property to store our data, to represent our data. So all these particles can exist in superposition. So this is what I explained. So superposition means diagonal spin or diagonal polarization. So if you have two quantum particles, sorry, single quantum particle, you can observe superposition. But if you need to observe entanglement, at least you require two quantum particles, because For entanglement, you need at least 2 quantum particles, and you can create entanglement for 100,000 or billion quantum particles. Billion quantum particles. So imagine if you have two quantum particles, if it is stating to state 1, this will also state 1. Imagine if you have 10 quantum particles. If you have 5 quantum particles, if you are changing one quantum particle in 1, then remaining all quantum particle will point to 1. So this is like a synchronized process. So this will exactly look like military march past. Are you able to imagine what I try to represent? If you have n number of quantum particle, if all quantum particle in entangled state, it will act like a synchronized way. So if you turn one quantum particle into 0, all other quantum particle automatically turn into 0. So this is the power of quantum computer. Okay, if you understand, so this will work like a army, very huge army. Okay, if you have a very small group.
Excuse me, sir.
Yes, ma'am. Yes, ma'am.
Sir, I have a doubt. So, if
Yes, ma'am.
two electrons, you said the handful are entangled. So, if two electrons are there, automatically they will be entangled, or we
We
have
need to make
to,
it, ma'am. We need to make.
we need to make it. Okay.
We need to make in laboratory condition. Once you completed entanglement, you can separate.
Okay. Okay, sir. So, how do
Otherwise,
we
you
do
can
it, sir?
keep it. That information I don't know, ma'am, because theoretical physicists they will do.
Okay. Okay.
So
Okay,
you
sir.
just try to understand this concept. If you have two electrons, you can make it entanglement state. Then you can do calculation.
Okay, sir. Thank you.
Yes, ma'am. You can extend up to 100 electron. You can extend up to 1000 electron. So this is the motive. So this will serve like an army. So army is very powerful. With the help of army, you can do anything in synchronized way. So once you have handful entangled electron, you can do calculation. Now IBM reached 1024 qubits. In India, IASC they built up to 4 qubits. You look at the difference. Using superconducting architecture, the same architecture, uh, IBM, they able to achieve 1024 qubits, where in case of India in IIC Bangalore, they able to construct only 4 qubits. So Indian government target is within 10 years, in 2030, okay, our mission is to build 50 qubit system. 50 qubit system using superconducting architecture. So this is the state where we are lying. We need to go long way. Okay. So once you have this entangled qubits, you can go for quantum algorithm. Now quantum algorithm will use quantum logic gates, which is similar to classical logic gates. Classical logic gates. So normally classical logic gates, we have OR gate, then we have AND gate, then we have NOT gate. Okay. So similarly, we have different version of quantum logic gates. If you understand these logic gates, you try to relate with quantum. So by using all this stuff, what is the advantage we will get? We will get computational speed up. The computational speed up will be 100 times faster. So sometimes 1000 times faster, sometimes 10,000 times faster. Imagine in classical, if you're getting 5% or 6% speed up, this will be great, remarkable achievement. If you're able to achieve 10,000 times faster computation, you can do marvelous things. So for this example, I need to showcase one reference. So Google Quantum Supremacy. You will have this video. You will have this video. I'll share this link in your team. You just go and look at this. Where is the chat box? There is no chat box in this MS team. Can I share?
Yes, sir. Yes. Option is there.
Where's home view? Can anybody message in chat box so I can see?
Just I message, sir.
I think chat is disabled. Okay, no issue. I will share this link later. Right? So no need to waste our time. Anyway, I'll share.
You share to me, sir, and later.
Later I'll share, definitely.
Then I will share to the person.
So Google demonstrated one very hard problem. So what they did, they put in world powerful supercomputer. World powerful supercomputer. This computer nearly will take 10,000 years to solve that problem. Solve that problem. So what Google scientists did, they took the same problem, they put in Google quantum computer, and that computer gave results within 300 seconds. So within 3 minutes, that computer able to solve very hardest computer problem. So this is the potential of quantum computer. You can able to think about this. So what is the very complex problem you have in your domain? Either you are from physics background or chemistry background or computer science, EC, triple E, whatever the background you have. Your domain contains very complex problem, very hard problem to compute. Okay, you can took those type of problem and try to solve in your quantum computer. So this is the possible way we need to think. Okay, so what is the advantage of doing in quantum? One thing, you will get exceptional computational speed up. The second thing, you need to do measurement. Okay, so what is the meaning of measurement in classical physics lab or chemistry lab? Okay, if you do measurement, what it means, you are doing observation, you are taking readings. Okay, after doing multiple readings, you will get a result. You are able to know what is the reason behind it. But in quantum, if you do measurement, quantum states will collapse. Are you able to recall the previous slide? Once you try to look at your quantum experiment, you try to observe, you try to measure, quantum state will collapse. It will appear like a particle. It will appear like a particle. So you'll get binary result. You'll get binary result, either 0 or 1. Either 0 or 1 you'll get. Okay, so this is the basic difference between classical and quantum. In classical, how many times you are doing measurement, the experimental setup won't get disturbed. Okay, but in quantum, once you try to do measurement, that quantum state will get collapse and you will get only binary result. You won't get any quantum state. The advantage is you will get high probability with very high accuracy. With very high accuracy of your result, you can get. by using quantum algorithms. So now you are not able to surpass classical algorithm, but it is proven. Theoretically, it is proven, but practically, it will take another 10 to 15 years. So if you want to work in quantum computer, you need to wait another 10 to 15 years to do a real-time problem. Now you can do toy, toy kind of problem, or you can do toy problems. For experimental purpose, you can do, but if you want to solve the real-time problem, we need to wait for another 10 to 15 years because hardware is not evolved. Hardware is not evolved. It is an R&D. It will be in R&D for next 10 to 15 years. Okay. So to maintain this hardware, we need to maintain ultra cold temperature. We need liquid nitrogen to slow down the quantum particle because electrons always in motion, random motion. We need to slow down that motion by bringing down the temperature so that we need to maintain absolute zero temperature. Absolute zero temperature. So that is why we have this engine shield. So this will cover your entire quantum computer. Here I can find the processor. So this processor contain electron. So this is how your quantum computer architecture will look like. Okay. So how will you manipulate your electron? How will you control electron? By sending microwave pulses. Microwave pulses. So you're sending microwave pulses through all these wire cables. Okay. So this will minutely will control your electrons. So this is how we are able to control electrons, be able to process. Okay. So otherwise you can use laser beam in a trapped ion. So it will come under photonic computing. So China heavily invested in photonic quantum computer. So each and every computer architecture have own advantage and disadvantage. So this is how quantum computer works. So if you have any doubt, you can ask me. Open for questions. Is it clear? Shall we move?
Yes, sir. Yes, sir.
Okay, great.
Yes, sir.
So we'll discuss what is the difference between classical bit and quantum bit. This is about classical bit. So binary digit. Okay. So bit stands for binary digit. This is stage value 0. This is value 0. This is value 1. This is value 1. So what it means, if you have one register or if you have one flip-flop or if you have one transistor, you can store either 0 or 1 by changing your energy, by charging it, by discharging it, you're able to differentiate between 0 and 1. But if you have one single device, you are able to represent only one value at a time. Are able to get idea? So if you have one device, able to represent only one value at a time. So this is the restriction we have in our classical electronics. Okay, classical electronics, all these devices. But in quantum, qubit stands for quantum bit. Okay, quantum bit can exist in superposition. So this is the meaning of psi. So this is the special symbol we need to represent quantum state. Okay. So this will exist in superposition. So this will exist in superposition. This is called psi. Okay. So consider this is like a needle. So it will move from 0 to 1. Imagine it is like a gauge. Okay. So here you have electron. This electron will move from this arc to this arc. Okay, it will move continuously and randomly. So what is the meaning of it? It is in superposition. It is in superposition between 0 and 1, not like classical. In classical, if you have a single device, you can represent either 0 or either 1, but you have combination of both 0 and 1. Okay, so this is the both combination of 0 as plus 1. So within a single device, you can represent two values at same time, like a mixture. So this is not possible in classical. In classical, only one value you can represent, but in quantum, you can combine these value and you can represent as a mixture. Okay. Suppose if you have two qubits, you can represent 0, 0. If you have two flip-flops, you can represent this combination. Okay. But if you want to represent 0, 1, you need to wait for one more cycle, instruction cycle. But in quantum, at the same time, you can represent 0, 1. At the same time, you can represent 1, 0. At the same time, you can represent 1, 1. So you can represent all four possible combination in quantum, but in classical, you can represent only one of these combination at a time. So this is for quantum, this is for classical. Are you able to understand this slide? So if you want to represent four combination, if you have two devices in classical, you need 4 instruction cycle, 4 seconds. But in quantum, if you have two qubits, within a single second, you can represent all your data and you can compute your values simultaneously. Okay. So if you have 3 qubits, you can represent 8 combination at the same time and you can get the result at the same time. So this is the fundamental difference between quantum bit and classical bit. So if you want to compare, this will take 8 seconds in classical. This will take 1 second in quantum. Is it clear? Shall we move? Because this slide is
Yes, sir.
important.
Yes.
Okay.
Yes, sir. Yes.
Thank you all. Thank you all. Thank you all. So compare like this. If you have one quantum bit, you can represent two states. Okay. Adding one more qubit will double the number of possible states. So I am just adding one more quantum bit. The increase is exponential. 2 qubits, 4 states. Okay. 3 qubits, 8 states. 4 qubits, 16 states. So likewise, you can represent more number of data simultaneously. You can do computation also. You are able to get the result simultaneously. Now, if you have 50 qubits, you can represent 1 followed by 11 zero states. That much of information you can represent with the help of only 50 qubits. Imagine if you have 50 bits. Imagine if you have 50 bits. How many information you can represent? Very, very less. Very, very less. Like a text file. Like a text file. Even text file won't fit within a 50 qubits. Sorry, 50 bits. Okay. So what you can understand from this slide with previous one. So look at this point and try to relate with previous slide. Where it is related. I can give the clue doubles.
Making the transistor
Oh,
size small, sir.
X, ma'am, exactly. It is like related to Moore's law. So what Moore's law do? Each and every 2-year computation power should get double. So you can indirectly achieving that by adding one more qubit. So this is how quantum computer will save this Moore's law. Will save this Moore's law. So this is the very important problem we are addressing. By retaining Moore's law only, semiconductor industry going to thrive. So depends upon semiconductor industry success, CS and IT industry will survive. Each and every year, they can take challenging projects. They can go for advanced project. So CS and IT industry will help to increase all productivity across all domains. So if you understand this, we can go for demonstration. IBM Quantum. So if you have pen and paper, you can please note out. There is a link called IBM Quantum. So make down this link. Note down this link. Is my presentation visible?
Yes, sir. Yes, sir.
Okay, thank you. So in this web link, you can click sign into platform. So it is in right side, top right, sign into platform. So click this link. So I need to fill 3 to 4 pages. Maybe I can log out from my profile. Then you can understand how it works. So that page is appeared in this dashboard. So what you need to do, you need to use your Gmail account to log in. If you have Gmail account, please create a IBM ID. It will ask 3 to 4 pages forms. You need to fill that. Once you completed, you will have login. So I created my account using my Gmail account. So this is how dashboard look likes. Okay. So this is my dashboard. It will be little different from you. So each and every month, IBM giving 10 minutes of quantum computer access through cloud. Okay. So 10 minutes is more than enough. Normally your calculation will take 1 or 2 seconds only, right? 10 minutes is more than enough. Each and every month they will give 10 minutes access for a real quantum computer. Okay. You can do simulation also. Simulation unlimited time you can use. No issue. But real quantum they will give only for 10 minutes. So for me, it is more than enough for research purpose. And you can go in learning tab. So I want to highlight IBM free courses. So click in the explore all courses and tutorials. So you can find varieties of course like this. I recommend the first course, Basics of Quantum Information. This is very fundamental and preliminary. Okay, so note down this course, Basics of Quantum Information. Once you completed this course, you can go for advanced courses like Fundamentals of Quantum Algorithm. Then you can go for General Formation of Quantum Information, right? Then you can go for Quantum Computing in Practice. Then if you are interested in business perspective, you can go for Business Foundation. So this VAD stands for Variational Algorithm Design, which is equivalent to Quantum Machine Learning. So if you are interested in machine learning, complete this first course. So complete this first course, then go for other courses according to your choice. So I recommend this first course, Basics of Quantum Information. Right. So I'm clicking first course, and you can see the course titles, right? So each and every course contains textbook as well as the video. You can download material over here. So each and every video contains slides. So it is easy for you to prepare. Okay. So this course is taught by John Waters. Oh, he is the professor working in Canada. For past 30 years, he is handling this quantum course. Okay. So it will be little difficult for the people who don't know about quantum in between. So you need to watch this video multiple times. You need to pause. If you don't know, you need to come back to Google. Then you need to search. Then you need to retain your video. So this is how you need to study quantum, right? So little tough for the beginners, but even though we need to study in our own way, right? So either you can watch video or either you can go with text, whichever is easy for you. So I recommend both. So once you read text, make notes, then watch video. Otherwise, you watch video, make notes, compare with this text. Okay. So each and every module contains quiz, contains example. So it is based upon Python. If you know Python, you can work on these programs, this software, right? So everything is given easy for you. Okay. Once you completed, you can check mark this box. Okay, mark as completed. You can move to further titles. Okay. So this is about free courses available, how you can study self-paced manner. Then I recommend Composer. So this is an online tool where you can construct quantum circuit. Okay. So initially, this Composer will appear like 4 qubits, 4 classical bits. I'll go very slowly, right? I hope everyone new to this domain. Right? This is how it looks like. You need to click Composer. So if you click Composer, it will appear in this way. So here you can notice this is the quantum bits. Q stands for quantum, C stands for classical. So for each and every quantum bit, you need classical bit to do measurement. So this will store your quantum value, okay, at end of your experiment. So you need to do some calculation. Okay, after calculation, you need to do measurement. So measurement will give binary result. Okay, so C always store classical value, binary value, right? So what we'll do, we'll select quantum bits and we will delete. So just click this bit, delete, click this bit, delete. Do the same for classical. So I maintain one quantum bit, one classical bit. Are you able to follow? If you are recording this video, please keep it, then share with the participant. Later time they can do on their own. Okay. So you need to go for view section where you can select your panels. So I selected graphic editor and QSphere for easier understanding. Okay. You can select code editor. Then you can select state vector. Right. So each and every panel will give more information about your quantum circuit. Then you can select probabilities. You can select probabilities. Now I have the complete version. So initially it will show all this view. What I suggest you for understanding, we'll do one by one. Okay. So disable probabilities, uh, disable state vector, disable code editor. So keep only graphical editor and QSphere. Now it will look like a musical notes. You need to drag and drop your quantum gates over this circuit and you can see output over here. So this sphere represents electron. Okay, imagine this is a quantum bit. Quantum bit contains two levels. So northern hemisphere, southern hemisphere. So we divide our electron state into two levels. We associate our data into these two levels. So north for 0, south for 1. Now the circuit is empty. If circuit is empty, it will represent state 0. So this is the meaning of uh, over here. You can see the output over here. It is in gray color. So you can zoom a little bit. Yes. Now circuit is empty. Q0, nothing is there. C1, nothing is there. If you look at right side, you can see this circle. So this is called phase disk. You can see output quickly. So here you can notice probability of state 1 is 0%. So look at the blue dot. Okay, probability of state 1 is 0% because it is in state 0 now. Okay, now look at this sphere. This is called block sphere. Okay, now your electron is stating in north pole, pointing to north pole. So this represents state 0. Now move your mouse over this blue dot. You can see information like this. So stage 0, probability is 1. Okay. Now what we do, we try to drag and drop NOT gate. So this is the NOT gate. Okay. So drag and drop NOT gate over here. Now your output is changed to blue color. Why? The value state 0 converted into state 1. Are you able to see the downside? The electron is moved from north pole to south pole. Now it is pointing south pole. Now what is the state of being 1? 100%. Probability is 1. So is this clear? All of you able to follow? Am I audible?
Yes, sir. Yes, sir.
Okay, great.
Yes, sir.
Okay. So now what I do, I try to drag and drop one more NOT gate. Now tell me what is happening. So this is state 0. If you apply NOT gate, now it will move to state 1. Okay. Again, if you apply NOT gate, again it will move to state 0. So that is why you got output in state 0. So this representation is called direct representation, direct notation. So this bar and this angular bracket. So this is called bracket notation. Bracket notation. You can reverse this notation in this way also. This is get bar notation. So it is reverse. You need to interchange get bar notation. Okay. So if you drag and drop one more NOT gate, what will happen? Again, it will move to state 1. From 0, state 1. Okay, from state 1 again state 0. From state 0 again state 1. Able to get the logic, how to predict the output after each and every NOT gate? Is it clear? If you have doubt, you can ask me. Able to get the idea? Initially, your quantum state will be in state 0. You are applying NOT gate, first NOT gate. So this is the first NOT gate. You'll get state 1. Again, you are applying the second NOT gate. Okay, it will move to state 0 again. Again, you are applying third NOT gate over here. Okay, it will move to state 1. Is it clear? Shall we move?
Yes, yes, sir.
Great, sir. Great. Now what we do, we delete all these gate, select this gate, press delete button. So select this gate, press delete button, it will get deleted. Okay. Now enable your panel's state vector. Now you can see for a single qubit, how many possibilities? 2 possibilities, either state 0 or state 1. Now it is showing state 0 full amplitude. Okay. Now drag and drop NOT gate over here. Now the probability of state 1 is full because the signal for state 1 is now full. So this is how you're able to check how it is working for state vector. So apply 2 NOT gates which will cancel each other. The original state will retrieve back. So apply 2 NOT gates which will cancel each other effects. You'll get the original state. Okay. So select this NOT gate, delete. What do you do? Try to implement Hadamard gate. Apply Hadamard gate. Okay. This Hadamard gate represents equal superposition. Which will create equal superposition. Superposition. So 50% chance for 0, 50% chance for 1. You can observe from this block sphere. So at the same time, so this is a single device, single qubit. Okay, or you can say this is a single device. Single device able to represent two values at same time, which is not possible in classical. Okay, here we mention quantum state. Here we mention quantum state. Able to get the idea? So at the same time, it represents both 0 as well as 1. And what is the state vector? 0.707 for 0, 0.707 for state 1. Now you enable probability. What is the chance of 0? 50%. What is the chance of being state 1? 50%. So there is a slight difference between state vector and probability. So if we got much
Sir,
more
excuse
time,
me.
yes, sir.
How do you get that amplitude 0.707, sir?
That is what, sir. It is a little lengthier topic. I tried to cover because we have very limited time.
Okay, okay.
I will cover, sir. I tried to cover. So normally, alpha stands for stage 0 signal strength. Beta stands for uh, state 1 signal strength. Okay. Imagine if both are equal. Imagine if both are equal. Okay. What you'll get? You need to represent with 1 over root 2. You need to represent with 1 over root 2. So this is the logic behind that thing. So what you need to do?
Okay, yes.
So alpha state 0 plus beta state 1. So note down this equation.
Yes.
If it is in equal superposition, the alpha become 1 over root 2, the beta become 1 over root 2. If you want to convert your quantum state amplitude into probability, you need to apply modulus, you need to do square. So if you apply modulus, if you do square, you'll get 0.5. So this value 1 over root 2 is nothing but 0.707.
Okay, yes, sir, yes, sir.
Now it will become equal to 1. So if you add 0.5, it will be 1.
Yes, sir, yes. Thank you,
Great.
sir.
Thank you. Okay. Now we try to understand the Hadamard gate. If you look at the output, you can easily see half filled. So 50% chance for 0, 50% chance for 1. The probability of state 1 is 50%. Okay. So this is an example for superposition. If you want to create superposition, you can use Hadamard gate. Hadamard gate will act like a equal fair judge. 50% chance for 0, 50% chance for 1. Now, what we try to do, we try to create one more qubit, one more classical bit. If you have 2 qubits, how many combination you can represent? If you have 2 qubits, recall that slide.
2 power 2,
4.
4.
4.
Yes, sir. Yes, ma'am. 4 combination you can represent. Oh, this is not working. So maybe I can zoom a little bit. If I am zooming, are you able to see that effect?
Yes, yes.
If I am zooming, the same effect will appear, right, sir?
Yeah, we are
Yes,
able to
sir.
see.
Okay. So now you compare, we have 2 qubits. Okay, circuit is empty. So everything is 0, 0. Everything is 0, 0. So you have 4 possibility 0, 0, 0, 1, 1, 0, 1, 1. Because circuit is empty, you have full signal strength for 0, 0. Able to see? Now it is little bit changed to 0, 0 instead of 0. And also probability. If you measure now, you will get value 0, 0. Now what we can do, we try to incorporate not getting Q0. Now we try to change one of the qubit value into 1. Now what is the output you'll expect? You'll get 0, 1. Are you able to see? 0, 0 means both qubits are 0. 0, 1 means the first qubit is 1. That is why we got combination as 0, 1. Now you measure the circuit, you have probability of getting 0, 1 as result. Able to get the idea? Now if I am bringing one more NOT gate for Q1, what is the output you can expect?
1
Both
0.
qubits,
Oh,
yes ma'am,
oh.
1, 1. Able to see the output. So this is how you need to relate each and every gate operation. You need to visualize with your mind. Okay. Now what I do, I try to bring Hadamard gate for Q0. Now what will be the output? Can anybody say? Can anybody say? Q0 now have two options. Either it could be 0, either it could be 1. Q1 always 0. Q1 always 0. So you have either 0, 1 or you can have combination 1, 1. Are you able to get the idea? Now look at your output. Either you can get 0, 0 or 0, 1 because one of the qubit is having capacity of both values where Q1 always have 0. Sorry, I wrongly wrote that values. Once again, I will explain. So state 0 for Q0, state 1 for Q0. After applying Hadamard, it will branch into two possible values. Either could be state 0, either could be state 1. But what is the value for Q1? Only state 0. Able to get. So imagine you are representing value Q1, Q0. Okay. So what is the first value for Q0? 0. Okay. So what is the value for Q1? 0. So this is the first combination. So this is Q0. This is Q1. Are you able to get the idea? So what is the next possible value? Q1 always 0. You write 0. But what is the second possibility of Q1, Q0? State 1. So that is why you got 0, 1 combination. Okay. So what about third combination 1, 0? 1, 0. Q0, it is 0 possible. Q1, it is showing state 1, which is not possible, which is contradicting. Able to get the idea? Able to get the idea? Why 1, 0 you are not getting output? Why 1, 1 you are not getting output? Because Q1 always 0. Where in case of Q0, either you can get 0, either you can get 1.
Yes.
Okay. Suppose if you drag and move Hadamard to Q1, now your combination is shifted 0, 0 and 1, 0. Now Q0 always becomes 0, Q1 might be 0 or 1. So restricting all combination into specific combination. Okay. Now if I am applying Hadamard gate for Q0, what it means? What it means? It will generate all possible combination at the same time. Now see the amplitude 0 0.5, 0 0.5, 0 0.5, 0 0.5. What is this probability? 25% of 0, 0. 25% of chance for 0, 1, 25% chance for 1, 0, 25% chance for 1, 1. So this is how we need to visualize quantum bits. Classically, it is not possible. You can represent only one combination at a time. But here you can represent all combination. You can do process simultaneously. You can get the result also. If you do measurement, you will get only one probability. You will get one probability 100%. So this is what here. This is the measurement. If you do measurement for 2 qubits, okay, you will get only one output. We got only 0, 0. Are you able to understand? If you do measurement, you will get only one value, like binary. So right here, I will stop my session. If you want to interact, if you have any question, you can ask me.
Sir, do you have any idea about Bloch-Spear notation, sir?
Yes, sir.
Bloch-Spear notation?
Yes, sir. Yes, sir. Bloch-Spear notation I have. Shall I
Yes.
take Bloch-Spear?
Yeah, for few minutes.
Yes, sir. I could spare. I have very easiest PPT because I know this is pain point for all beginners to understand Bloch-Spear. I have a meeting at 12:30, so before that I try to cover. So this is the Bloch-Spear. This is a sphere. Okay. So sphere
Yes.
having radius 1, which is called unit sphere. Okay? Like a unit circle, we have unit sphere, right? So what we are doing, we are dividing this Bloch-Spear into 2 levels because we try to represent qubits, quantum bit, quantum bit. So bit stands for binary logic. Binary logic. So that is why we divided the sphere into 2 halves. Okay, the equator exactly divides sphere into 2 halves to represent 2 level system, either 0 or 1. Okay. Now what we are doing, we try to create 3 axes, Cartesian axis, x, y, z, right? And we are referring 2 extreme points. So these points are extreme, okay, like polar points, North Pole, South Pole. We are mapping our value, binary value in these polar points. This become quantum states. So North Pole will act like state 0, South Pole will act like state 1. Okay. So these points are called pure states. Across the sphere, across this surface, wherever it is touching, okay, it is a pure state. Inside your sphere, it is a mixed state. So imagine a point, okay, which is inside your sphere, anywhere, it is in mixed state because it is in superposition, not exactly in 0, not exactly in state 1, right? So try to create a vector from state origin. So try to create a vector from origin pointing to electron. So this electron is inside your sphere, not in the surface also, inside this sphere, right? So slice that sphere into xy plane, okay, try to project a line from that point. So this is called projection. So this will touch with your xy plane, okay. So make one more projection towards to your origin. So this will create a right angle triangle, okay.
Oh, yes.
Once you got right angle triangle, you can convert Cartesian coordinate into polar form.
Yes.
So how we can achieve? By creating 2 angles. So we'll get one angle theta and one angle psi.
Oh, okay, yes.
Now we can rewrite all this stuff into polar form, polar equation. So psi is nothing but your quantum state, your quantum state. This can be explained with two components, cos component and sine component. This is Euler component. Okay, so substitute value, if quantum particle, okay, electron pointing to north pole, deta equal to 0. So substitute value, what you will get? Deta equal to 0, cos d2 by 2, sin deta by 2, you will get only cos component. So sine will become 0. So this is equivalent to identity gate. If we do nothing, the electron will remain in the same state. Are you able to understand this concept up to this? Is it clear? Okay, great. Now what we do, we try to give value for deta. Instead of 0, substitute pi. If you apply pi angle for deta, where it will go? If you apply pi angle for deta,
Y, Y,
yes ma'am, yes ma'am,
at the
it will
Y
go
side.
for z.
G.
It will go for z, rotation, pi angle. Able to get the idea?
Yes, yes.
So if you apply pi angle, it will move from north pole to south pole, which is nothing but NOT gate. What we see in previous demo, the same thing you can see in equation form. So this is how, if you apply NOT gate, transition will happen from north pole to south pole. Okay, if you are in state 1, if you are applying NOT gate, d equal to pi, again it will move to state 0. So if you understand this, we can go for d equal to pi by 2, which is the half the value. Now it will go for x-axis. So this is what happens. If you apply NOT gate, move from 0 to 1. If we apply Hadamard gate, it will go equal superposition. So this is an example for Hadamard gate. Able to get the logic?
Yes, sir. Yes, sir. Thank you.
Great, sir.
Thank you.
Great,
Thank
great.
you so much. Yes. Can you
So,
share this?
like, I
Yeah.
will share. Okay, I
Yes,
will
sir.
share. So we can form multiple axes. So we can represent in matrix. So easier way to understand what is happening. So this is the link where you can practice block sphere, where you can have hands-on. X gate, again apply X gate, it will go to state 0. You can apply Hadamard gate, it will create equal superposition. Again apply Hadamard gate, it will go back to state 0. I'll share these slides with you, no issue. So if you want to connect with me, this is my social media ID.
It's not visible, sir.
Yes, ma'am, I will share, try to start. So if you Google my name, you can easily get. So this is my ID. So you can follow me or you can give connection request. I try to respond as much as possible. If I am not able to respond, I will try to connect with my team. I will get back to what you are looking for. Okay, thank you all patiently listening for this 1.5 hour. I try to touch up, not able to cover. I try to touch up about quantum. Thank you all.
Dear participants, if you have any doubts, please raise your hand. Yeah, otherwise we conclude the session. Okay. So today's session is very wonderful. So you have explained in very practically, which was very useful. So now we are going to conclude the session. I would like to invite Bhuvaneshwari ma'am, assistant professor in physics, to deliver the vote of thanks.
Am I audible, sir?
Audible, ma'am, audible.
Yes, sir. Good afternoon to everyone. As we come to the end of this enlightening 7-day online faculty development program on quantum computing for the next generation, jointly organized by the Department of Physics and the Department of Computer Science, Rathinam College of Arts and Science, under the DPT Star College scheme. I would like to take a moment to express our gratitude. Firstly, a heartfelt thank you to our distinguished speaker, Dr. Jaikumar, for sharing your expertise with us, sir. Your session have been both informative and inspiring. We truly appreciate the time, effort, and knowledge you have shared with us throughout this program, sir. Thank you. I would also like to extend my thanks to our institution leadership, Dr. R. Manikam, CEO and Secretary, Dr. S. Balasubramanian, Principal, Dr. S. N. Suresh, Vice Principal, Dr. KPV Sabaris, Dean of Research and Development, for their contribution support in making this program a success. Your encouragement and vision have been instrumental in organizing this type of event. A special thanks to the heads of the organizing department, Ms. D. Uma Maheshwari, Department of Physics, Dr. S. Raja, Department of Computer Science, and Dr. D. Velumani, Department of Computer Science, for your dedication and hard work in making this program a success. Your leadership and commitment have ensured that everything went smoothly. I would also like to thank all the department heads and faculty members for their active involvement and enthusiasm. Your engagement has truly enriched this program, and we hope you leave a deeper understanding of quantum computing and artificial intelligence. I would like to take this opportunity to thank all the active participants and thoughtful contribution which have significantly enhanced our collective learning experience throughout this program. Finally, a heartfelt thank you to everyone behind the scene, the organizing team and support staff for ensuring everything ran smoothly. Your efforts have not gone unnoticed. Once again, thank you to all the eminent speakers for your valuable contribution throughout all the 7 days FTP program. We look forward to seeing you all in future programs, and we hope you continue to explore the existing world of quantum computing. Thank you and have a wonderful day.
Thank you, ma'am. So thank you all of you for joining the today's sessions. I will post the feedback link very shortly. Please share your feedback. Thank you all of you once again.
Thank you, sir. Thank you.
Thank you, sir.